In this video, we look at the vibrational normal modes of water. Water is a planar angled molecule. There are 3 atoms, and each atom can be displaced along 3 different directions in space. Therefore, there are 9 total degrees of freedom. Of these, 3 are needed to describe translations, and another 3 are needed to describe rotations, which leave us with a total of 3 vibrational degree of freedoms. These 3 degrees of freedom constitute the normal modes of water. There are 3 normal modes. And here's how they look. The first mode involves a synchronous vibration of the 2 OH bonds, so they extend and contract simultaneously. This is called the symmetric stretch mode. And it occurs at about 3,657 inverse centimeters. The absorption into this mode is not very intense, since the transition dipole moment is small. The next mode also involves vibrations of the 2 OH bonds, but this time in opposite phase. So while one extends, the other contracts, and vice versa. This is called the anti-symmetric stretch mode. And it occurs at about 3,756 inverse centimeters. It is also not very intense. The last mode, number 3, is different. It involves the vibration of the bond angle, and it is called the bend mode. It occurs at about 1,595 inverse centimeters, so much lower than the other 2 modes. Also, absorption into this mode is intense. The reason for this being that the dipole moment varies substantially as the molecule vibrates. To induce allowed transitions in any of these modes, you need infrared photons, which have energies of a couple of tenths of electron volts, in our case about 0.1 to 0.5 eV. Each of these 3 modes can be described by a simple harmonic oscillator model with a quadratic potential. The displacement coordinates of these 3 harmonic oscillators are the normal coordinates. And they're designated Q1, Q2, and Q3. These are linear combinations of displacements of the various atoms involved in a normal mode, which are additionally weighted by the masses of the atoms. That's why they're not labeled X, but Q instead. Even though these normal coordinates are not easy to visualize, the important thing here is that they're independent. Therefore, the overall vibrational potential energy of water can be described as a sum of the potential energies of the 3 independent harmonic oscillators. Here's the expression. V of Q1, Q2, Q3 equals 1/2 K1 Q1 squared plus 1/2 K2 Q2 squared plus 1/2 K3 Q3 squared. Now, to describe a particular vibrational state, we need 3 quantum numbers, 1 for each harmonic oscillator. And they're called N1, N2, and N3, where each of those can assume values of 0, 1, 2, and so on. The total energy of a vibrational state is the sum of the energies from the 3 one-dimensional oscillators. So, E of N1, N2, N3 equals h bar omega 1 times N1 plus 1/2 plus h bar omega 2 times N2 plus 1/2 plus finally h bar omega 3 times N3 plus 1/2. This is for a general eigenstate. For the overall ground state, the energy E00 equals 1/2 h bar times omega 1 plus omega 2 plus omega 3. This is the 0-point vibrational energy of water. For water, it's about half an electron volt. The overall vibrational wave function describing the vibrational state is the following. Psi of n1, n2, and 3, variables q1, q2, q3. This wave function can be written as a product of the wave functions from the three individual oscillators. So this is equal to psi n1 of q1 times psi n2 of q2 times psi of n3 times q3. You can look at this as a three-dimensional harmonic oscillators, since there are three independent harmonic oscillator coordinates. In this sense, this is a very similar situation to a particle in a three-dimensional box. In summary, water has three normal modes with different oscillator frequencies and different transition intensities. Each mode is described as a one-dimensional harmonic oscillator, and the energy of the overall vibrational state is the sum of the energies of each of these modes. And the overall wave function is a product of the wave functions from these three different one-dimensional harmonic oscillators.